Hello, my name is José Álamos. Working with Peter Kietzmann, Thomas Schmidt and Matthias Wählisch, I will present our poster DSME-LoRa, a flexible Mac for LoRa. LoRaWAN is a cloud-based media access control protocol for constrained devices that defines an upper layer for LoRa, a long-range wireless modulation. The LoRaWAN infrastructure is centralized. In fact, a LoRaWAN network server controls media access and forward packets between end devices and the cloud. LoRaWAN networks impose strict restrictions on downlink rate in order to comply with regional duty cycle regulations. Specifically, some LoRaWAN networks restrict the number of downlink packets to 10 per device per day. End-to-end latency is unbounded because the schedule of downlink frames depends on downlink load. LoRaWAN does not support direct peer-to-peer communication. If two devices require to communicate, the network server must forward data between them. Finally, LoRaWAN communication requires a permanent infrastructure backhaul. Intermittent connectivity in the infrastructure stops data retrieval from and between end devices. All these limitations make LoRaWAN impractical for many control use cases. In order to overcome these barriers, we propose the usage of IEEE 802.15.4 DSME deterministic and synchronous multi-channel extension as an alternative MAC layer for LoRa. DSME networks can operate either on a peer-to-peer or cluster-tree topologies. The MAC initializes a beacon synchronized superframe structure that enables two transmission patterns. On one hand, CSMA-CA during a contention access period used mainly for MAC control traffic. On the other hand, multi-channel guaranteed time slots during a contention-free period. Superframes are organized in a multi-superframe structure in order to extend the number of available guaranteed time slots. DSME is very flexible. That means the number of superframes, the duration, and beacon interval can be configured in order to provide a balanced trade-off between association time, end-to-end latency, and network size. Therefore, the research question we try to address is, can DSME overcome LoRaWAN limitations to enable direct communication between LoRa nodes? In this work, we present a mapping scheme to operate DSME on top of LoRa devices. We define 16 orthogonal LoRa channels in the EU 868 band and map them to DSME transmission patterns. All channels use typical LoRaWAN PHY settings and constrain the duty cycle to 1 or 10%. We assign a channel of 10% duty cycle to the contention access period in order to relax restrictions on the transmission of control traffic. In addition, we propose the usage of the channel activity detection feature of LoRa available in common LoRa transceivers to assess clear channel during the CSMA-CA procedure. Alright, I would like to present our setup and results of our experimental evaluation. We evaluate DSME-LoRa using the OmNet++ simulator with the INET framework. We use the DSME implementation of OpenDSME. We also extracted the LoRa radio model from Flora, a LoRaWAN simulation model for OmNet++, and finally, we implemented a DSME-LoRa adaptation layer. We create a simulation scenario that consists of a single-hop peer-to-peer network with sensors and actuators. Each sensor transmits unconfirmed data to a subset of actuators at an exponential rate and in a dedicated guaranteed time slot. We define the size of the subset of actuators, namely actuators per sensor, as APS. We configure the superframe structures to 4 superframes per multi-superframe and set the duration to approximately 32 seconds. With these settings, the slot schedule repeats every 28 slots. The figure visualizes an example slot schedule for our simulation scenario. We assign a guaranteed time slot for each sensor actuator pair. The slot schedule is configured during initialization and does not change during the experiment. Please note that the device can only transmit or listen during one time slot. We simulate two networks with different numbers of sensors and actuators. We vary the transmission interval and the number of actuators per sensor between experiments and measure the time to completion. The results show time to completion only depends on transmission interval and number of actuators per sensor, and not on network size. In all scenarios, the time to completion is lower bounded by half of the multi-superframe duration. When the Mach-Q stress increases, either due to lower Tx interval or lower number of actuators per sensor, the time to completion increases. In scenarios where the Mach schedules faster than the transmission rate, the Mach-Q overflows. Therefore, time to completion sharply increases. Moreover, there is 0% loss in cases where the Mach-Q does not overflow, and nodes are compliant with duty cycle regulations in all scenarios. To conclude, DSME-LoRa enables long-range peer-to-peer communication. We learned from the experiments that DSME-LoRa is even suitable for networks with more than 100 nodes. We also learned that end-to-end latency is not dependent on the network size, but rather on the Mach-Q stress and superframe configuration. Our research agenda is twofold. First, we would like to adapt concepts by the IETF 6TiSCH group in order to enable IPv6 and multi-hop communication over DSME-LoRa. Second, we will port OpenDSME into Riot OS, the friendly operating system for the Internet of Things, in order to evaluate a DSME-LoRa deployment on real hardware. Thank you for listening. You can find our code and documentation in this GitHub URL.